Hi, in this lecture video, I will discuss Sp3 hybridization in greater detail, and I will also construct a molecule with Sp3 hybridization in it. So first, let's now go over Sp3 hybridization. So again, this refers to the fusion of one of the S with all of the 3p orbital in it, and this is why we call them Sp3. And Sp3 hybridization atom would then have the tetrahedral electron geometry. And this is how we can recognize whether or not if an atom has Sp3 hybridization by looking for its electron geometry. If it has tetrahedral electron geometry, because it has 4 electron groups surrounding the central atom, then that atom would then have Sp3 hybridization. For an example, in methane, the carbon is having an Sp3 hybridization. And so if we were to construct the Lewis structure of methane, this is what it would look like. A carbon with 4 hydrogen bonded to it. And we can see that this carbon right here, this has tetrahedral electron geometry. And because of it, it would then has Sp3 hybridization. And now, let's see what's happening right here in this Sp3 hybridization. So the carbon in Sp3 versus for each of this hydrogen right here, it would be involved in this bonding by simply using electron from its 1s orbital. So for hydrogen will be using the 1 electron from its 1s orbital in this bonding. As for the carbon, so initially, the orbital diagram of the carbon is that it has 2 electrons in the 2s orbital. And then here are the 3 2p orbital. So let's label them 2px, 2py, and 2pz. And now it has 2 electrons in it. So in the case of Sp3 hybridization, all of these 3p orbital right here are involved in this hybridization process. So basically, we will be combining these 4 orbitals together. And that's the meaning to Sp3 hybridization. And as a consequence, we'll be able to produce 4 hybrid orbitals. And these 4 hybrid orbitals right here have the same amount of energy. So we call them the degenerate orbital. And each of them will then be Sp3. So that's how we can label them. And so this carbon right here has 4 electrons. Therefore, the 4 electrons will then go into each of this orbital. And now, this carbon right here, essentially, it has up to 4 orbitals to form bonds. And now let's take a look at what the structure of each of these orbitals look like. So initially, the carbon, it has electron in its 2s orbital, and we know that with the 2s orbital, it is spherical with a 2 electron in it. And now with the 3p orbital, each of the p orbital look like this dumbbell right here, and this is what we have learned before already. And these are the 3 2p orbital. So initially, that's what the structure of this orbital would look like. But now, after this orbital right here have fused together already and undergo an hybridization to produce this hybrid orbital. This hybrid orbital right here that are produced basically have characteristics of both the s and the p orbital. And now they actually look like this. Each of them will look like this. So they have a big lobe to them and a smaller lobe to them. And that's what each of the Sp3 orbital would look like. So maybe let me draw this a little bit better. So this is basically how normally they would look like. There you go. And there are 4 of them. And now each of them would then have 1 electron in it. So here are the 4 hybrid orbitals. And these 4 hybrid orbitals right here meet together at the node in the middle. So basically they meet right here. And if you were to think about all of this orbital, so there are 4 of them, and they have to meet together at this joint right here, and that basically where the node would be. And now they have electron in them, and the electron would repel each other. So essentially we have 4 things that have to fit together, and they repel each other because they have electron in them. So this is what they're going to do right here. So because they have to fit together to produce the structure of this atom, and now they want to spread out as far from each other due to the repulsion of the electron, they will then have to adopt this structure right here. A tetrahedral structure. And so I'm starting by drawing a tetrahedral backbone right here. And now I'm going to begin to add in the orbital. So one of the sp3 orbital would go right here with one of its electron. And the other one would then go into the other axis. And that way it would be. And then for the other one, this would then go in here. And lastly, the other one, that would then go in the back. So that's how this 4 sp3 orbit right here fit together. And this then produce a tetrahedral atom. And this is the reason why that the tetrahedral atom would then have sp3 hybridization, because there has to be 4 of these orbitals that are similar, so that way they can repel and then producing this symmetrical tetrahedral structure right here. And the bond angle within them would then be 109.5 degrees. So this is what the carbon would then look like. And now, the carbon, as on the structure, little structure we have seen already, the carbon is then produced from 4 bonds with the 4 hydrogen. And we know the hydrogen is using an electron from the 1s orbital. And the 1s orbital is basically spherical with 1 electron in it. So that's what the structure of the hydrogen would look like. So here in this case right here, we then have 4 hybrid orbital from the carbon. And now this is where the hydrogen would be. So 1 hydrogen would then go in here. And now the electron would then pair together, and then that form the first bond between the carbon and the hydrogen. And the other hydrogen would then go over here, and this create another bond between this carbon and that hydrogen. And another one would then go over here. And lastly, another one over here, another hydrogen here. So the end, this is basically what the structure of methane would look like using the valence bond theory. So the carbon has this 4 of this sp3 orbital, and each of the hydrogen use electron from its 1s orbital. And now this bond right here, in organic chemistry, we tend to label bonds, and this bond right here is something that we would describe as a sigma bond. A sigma bond is basically a bond that is formed by the overlapping of the atomic or hybrid orbital, in which that they form from end to end fashion. So basically the ends of one orbital is overlapping with the end of another orbital. And that, if that is the case, that bond will be referred to as a sigma bond. So here in this case right here, the end of this orbital, of this sp3, so this is an sp3 orbital, is overlapping with the end of this orbital right here. So therefore the bond that is being produced between these 2 atoms right here will then be a sigma bond. So we will label this bond as the following. So this bond right here is a sigma bond. And the sigma bond, that's the symbol for the sigma bond. And to further describe this bond right here, it is formed by a carbon using its sp3 orbital to a hydrogen using its 1s orbital. So that's how we would label this bond. So it is a sigma bond involving the carbon that sp3 to the hydrogen using its 1s orbital. So in this case right here, we have 4 sigma bond. So another one right here. and another one right here, and another one right here. So all of this would be the sigma bond, and this is how each of them would be labeled.